Incoming antimatter. Around 800 light-years from Earth lies an invisible factory of antimatter, tirelessly producing high-energy positrons, tiny particles racing through the cosmos until they collide with our planet. Most of these incoming positrons pass by unnoticed, disappearing into our atmosphere without a trace. It wasn't until we began observing from space that their presence truly came to light. In 2011, NASA activated the Alpha Magnetic Spectrometer, a cutting-edge particle detector orbiting about 200 miles above us on the International Space Station. And what did it find? You guessed it, positrons. Scientists expected to detect some of these subatomic particles, but the sheer quantity was startling. Natural sources like radioactive decay and cosmic rays couldn't account for the overwhelming numbers. So where were they really coming from? Recent discoveries have pointed to the culprit behind this cosmic shower, a strange high-energy phenomenon known as Geminga. First spotted in the 1970s, this mysterious source of gamma rays has puzzled astronomers for decades. What exactly is Geminga, and how is it linked to the unusual flood of high-energy positrons bombarding Earth? I'm Alex McColgan, and you're watching Astrum. Join me as we explore the strange and powerful signals of Geminga, a mystery that's been shining in the astrophysical sky for generations. Geminga, the cosmic mystery, 800 light-years away. Geminga is one of the most intriguing objects in our cosmic neighborhood. Located about 800 light-years from Earth in the constellation Gemini, this strange body is a pulsar, the dense, rapidly spinning remnant of a massive star that exploded in a supernova roughly 300,000 years ago. What makes Geminga especially fascinating is not just its origin, but the unusual radiation it produces. Discovered in the 1970s as an intense source of gamma rays, Geminga remained a mystery for years because it was invisible in most other wavelengths of light. Its name comes from a playful mix of Gemini gamma ray source and the Milanese dialect phrase Geminga, meaning "it's not there," a nod to its elusive nature. Over time, astronomers learned that Geminga emits powerful beams of radiation as it spins, much like a lighthouse sweeping the cosmos. More recently, it has been linked to an even stranger phenomenon, an excess of high-energy positrons, the antimatter counterparts of electrons, detected near Earth. NASA's Alpha Magnetic Spectrometer aboard the International Space Station has recorded far more positrons than expected from normal cosmic sources. Studies suggest that Geminga's Pulsar 1 nebula, a vast bubble of particles surrounding it, may be a major contributor. As Geminga's magnetic fields accelerate particles to near-light speeds, some escape into space and eventually make their way to Earth. This connection between a distant pulsar and the antimatter raining down on our planet offers a rare glimpse into high-energy astrophysics. Yet questions remain. How exactly are these positrons produced? And could other unknown sources be at work? Geminga continues to challenge our understanding of the universe, a reminder that even 800 light-years away, cosmic mysteries can still touch us directly. What is a pulsar? A pulsar is one of the most fascinating objects in the universe, a highly magnetized, rapidly spinning neutron star that emits beams of electromagnetic radiation from its poles. These beams sweep across space like the light from a cosmic lighthouse, and when they pass by Earth, we detect them as regular pulses of energy, hence the name pulsar. Pulsars are born from the dramatic death of massive stars. When a star at least 8 times the mass of our Sun runs out of nuclear fuel, it undergoes a supernova explosion. The core that remains collapses under gravity to form a neutron star, an incredibly dense object packing more mass than the Sun into a sphere only about 20 kilometers across. In this collapse, the star's magnetic field is intensified, and its rotation speeds up dramatically. The result is a pulsar that can spin anywhere from once every few seconds to hundreds of times per second. Its magnetic field funnels charge particles toward its magnetic poles, producing beams of radio waves, visible light, X-rays, or gamma rays. These beams remain fixed in the pulsar's frame of reference, but as the pulsar rotates, the beams appear to blink on and off from our viewpoint, much like a lighthouse beam seen from afar. Pulsars are incredibly precise in their timing, making them valuable tools for astronomers. They help scientists study extreme states of matter, test the laws of physics under intense gravitational and magnetic conditions, and even detect ripples in spacetime known as gravitational waves. First discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, pulsars have transformed our understanding of the cosmos. They are both relics of stellar death and cosmic surrounding.